So we've already been doing this, so I don't expect us to have to spend a lot of particular time on this chapter. We have been using functions. Explain why functions are useful in structuring code. Employ top-down design. Define a recursive function. Now that's of particular interest. I mean, it's probably the only thing in here that we haven't hit already. On the other hand, you're probably not going to use recursive functions in your day-to-day programming unless you go off and to I don't even know how to say it. It's just a more complex way of thinking about things. There's an entire branch of programming called functional programming, where you try to avoid all use of state information of variables, and then you accomplish tasks using recursive functions. Explore the use of namespace. Define a function with required and optional parameters. Use higher order functions for mapping, filtering, and reducing. Now this is interesting stuff, and I actually have tended to skip past it in the past. We'll see. All right, so a function. What is a function? Packages an algorithm in a chunk of code that you call by name. And I suppose you can call it an algorithm. I figured that the algorithm was the recipe for doing it, and then your code was the product of the algorithm, the implementation of it. But anyways, what is a function in my book? It's a named block of code, right? It's a block of code that has a name so that you can call it by name. And so the function can be called from anywhere in the program's code, including code from within other functions. A function can receive data from its caller via arguments. In other words, you can pass arguments in, you can pass data in. When a function is called, any expressions supplied as arguments are first evaluated. This is a strange one, but I see what they're saying. And a function may have one or more return statements. Let's get idle going. And I did not mean to start Windows. Maybe on lecture R. I'm going to run with that. So anyways, we've seen functions before. Functions begin with a DEF keyword, have a parentheses and end parentheses, a colon, and then just like anywhere else in Python where you have a colon, the next line has to be indented. And so you can have several statements here. An entire block of code. A block of code can be 1 statement long, it could be 1,000 statements long. And then when your program is ready to invoke the function, it just uses that name. If there was anything defined in here, any parameter variables, we would need to fill the parameter variables with arguments. There aren't any in this case. So if we want to get strict about our definition of variables, a variable that is defined within a function is called a local variable. He's a local variable. A variable that is defined totally unindented outside of the functions is a global variable. If I come up here and I define a variable like that, that is a global variable. It is global because it can be accessed inside any function that follows. Now, the way we've been writing our programs for the most part is just to declare all of our variables as global, right? Because we write all of our code as unindented. And as Jason has pointed out, then if you're writing this in PyCharm, it gives you some warnings about global variables. So what we should have been enforcing or trying to get ourselves to do the entire time was to put everything inside of a functions, including our main code. What does that look like? Well, you could have some main code here. And it prints, you know, this is my main code. And then you have to have a way to trigger that. Two ways to trigger it. One that you're not going to want to do. But you could just run it. And once you've run it, the main code is ready to be run. Now, I don't know how this works in PyCharm if you get the terminal window where you could just do this. But once it's all loaded into memory and the functions have been defined, you can go ahead and run main. We'd rather main run automatically. And we did this a while back, but it requires the use of a specifically defined if statement, which uses double underscores. Those are 2 underscores, not 1. And so you write it like this: if underscore underscore name underscore underscore equals equals quote underscore underscore main underscore underscore end quote colon main, just like that. Now when we run it, it'll invoke our main module here, our main function. All well and good. And if we create another file that imports this file, it will not trigger that, which is also good, right? Because if you import code, you don't want it to automatically trigger some code when you're doing it. So if I had another function that did import lecture r.py, or is it just lecture r? R, like that. Now I forget. Print lecture R imported. But that's all it's going to do. Where did I save the other one? Okay, documents iCloud. I'm just going to call this one test because I'm not going to do anything else in this particular one. I'm going to close it as soon as I run this test. Okay, so when I run it, it does import my other file, but it does not trigger and run, this is my main code. Whereas if I had put my call to main right here, rather than blocking it off with that, then when I did import it, it would run that. And where to go? Did I already close it already? Nope. There we go. So now, as soon as it hit the import statement, it ran in here, it called main and print, this is my main code. And then it came back to our code and ran lecture R imported. So it's not a bad idea to go ahead and block off your main code like this. Just add some structure to it just to make sure that if you import your code in from another file, it doesn't auto run anything automatically. And then the rest of our code would be defined here. And then none of our variables are global unless we really want them to be, right? If I do y is equal to 2 and z is equal to 3, the definition of these variables do not conflict with the definition of those variables anywhere else. So for example, if I try to print out y here, I can't. Hasn't been defined as of this point. I'm not even calling my f, so I don't know if that's true. And I also have a sneaky feeling that it's going to go ahead and try to print out the number 2 there anyways, because Python is far more generous about what gets passed to functions in a lot of languages. Oh, here we go. All right, y is not defined. Whereas if I had defined y as a variable up here, it would be accessible. Y is accessible to every function. Even if I had just done this, it doesn't look like it's going to be applicable everywhere, does it? It's defined after these functions. However, what the program does is when it's launched, it runs through, it defines that, meaning it adds that function to its memory bank. It's ready to be called. It defines it, so that function is there in its memory bank waiting to be called. And then, okay, now we're going to set this global variable equal to 2. And then we're going to come in here and we're going to run main. And so main comes in here, and now this variable already is defined. And so my F is going to be able to find it. One interesting thing about that, what would happen if I set y equal to 100, but then we're resetting it to 2 before we call my function? And in my function, we come in here and we print y. Is it going to print out 2 or is it going to print out 100? I think I know the answer, but I'm going to run it first so that I don't speak falsely. It printed out 100. Why did it not print out 2? If you want a function to be able to modify the content of a global variable, you have to use a special keyword. I think I'm going to erase that. Erase these two things. And I'm going to set this up back the way we more traditionally think of global variables as being defined above everything. As a matter of fact, we have one called X up here. So I'm just going to run with that one. Okay, so I'm going to write a function called change underscore X. And what does it do? It changes X, adds 1 to it. How about that? And so down in our main code, we're going to print X. We're going to call change X. And we're going to call print X again. We're going to see if X actually does get changed. And spoiler alert, it does not. Local variable X referenced before assignment. Well, that's interesting because it is not, is it not defined right here? Forgive me while I stare at that. Well, isn't that weird? It's able to print X here. It didn't like me adding 1 to it. Something particular about that syntax it didn't like? Alrighty. Well, it's almost proving the point that I wanted to make anyways, which is if you're going to use this global variable and you want to change its value, you have to prefix, you have to define it according to this function as being a global. It's saying, by the way, we're going to be talking about X, but it's really a global variable. And it's funny you have to do this because as we've already seen, if we try to print X, if we use X, we don't have to do this step. But if you want to change X, you do have to use this step. So now when I run it, change X is actually able to modify that variable, whereas it was unable to do so before. which is why when we printed out X here, we got 2. And then we called change X. X was incremented by 1. And then we printed it out, it said 3. And so you saw that. You saw that if I do something like this, but if we set y equal to x there, is it going to complain about that, saying that x is uninitialized, or is it only when we try to modify it? It's only when we try to use it to modify, right? Like that. It will not let us do that unless we have the statement global x in front of it. So that's what the global x statement does, is it says allow this module to change the specified global variable. All right, now I did talk about global variables for a good long time, and honestly, you should try to minimize their use. A well-written program does not rely upon global variables. Instead, all the data is passed in as arguments. How do you pass in an argument? Well, let's write a function that takes an argument. Def my function 2 is going to take an argument called name. And so it's going to print parentheses, hello, end quote, or common name. So down in here inside main, we're going to call that function, but we have to provide some data. If we call this and it doesn't have an argument, this is the argument, this is the parameter variable. So name is the parameter variable. Joe Bob is the argument that is passed to the parameter variable. So when it runs, we should see it say, hello, Joe Bob. Now, one of the statements in the PowerPoint is when a function is called, any expression supplied as arguments are first evaluated. What does that mean? Well, here we're passing in, a string literal. Where'd it go? Right. However, this could have been an expression, right? We could have had first name is equal to Joe, last name equals to Bob, and instead of printing Joe Bob right there, we could have had FN plus a space plus the last name, and that gets evaluated. This expression gets evaluated before this value is copied into this variable. It's very important to remember, especially if you've done programming in some other languages, that Python is a pass by value or a pass by copy language. What does that mean? It means that whatever is being passed in as an argument is copied into that variable. If I call my F2 here and I pass in just the first name like that, this variable is not equal to that variable. These are not the same variables. This is a completely different variable. I usually use the metaphor that this is like you hand him a copy. So like you have your thesis paper and you take it to somebody and you hand them a copy of it. You don't trust them with your original thesis, because what if they change your thesis paper? Then it's gone, right? You have no recourse to it. But instead, the act of sticking this in as the argument and letting it be copied into here means that your original data is safe. And we could prove that point. I'm going to write a function called change. It's going to take a variable and it's going to, I've already used X somewhere. right? It's going to take a value and set it to something. And so down in here, we're going to set a variable. We're going to even try to confuse ourselves and create one with the same name. So I have v is equal to hello. I call change, and now I'm going to print out what v is. Is it going to say hello, or is it going to have changed it to hi? And it's actually going to be hello. So print in change v equals, end quote, comma, v, right? We're going to see the contents of v there. And then in main, v equals, end quote, comma, v. We're going to see what it is after the call to change. And so in change, v was set to hi, but once we get back from there, v is still equal to hello. That's because these are two entirely different variables. This variable's value got copied into here because Python is a pass by copy, a pass by value language. The argument is copied into the parameter variable. They are not the same thing, even if they have the same name. In some languages, you could say, this is a reference to this. And so if you change it, it's actually going to change the original variable that was passed in. Python doesn't have that ability. If you want to be able to change something like that, you got two choices. One is you make it a global variable, or the other is you pass it back. What does that mean? I could do this. I'm going to call it change2. We're going to set v equal to some variable. Forgive me for just copying and pasting that line. But then we're going to return that value. And so down here, when I'm ready to invoke it, I'm going to call change2, but I'm going to store its return value back into itself so that when I print out the variable, now it's going to say, what's up? Right? So in change, v was high. That's true because it was set to high, and then we printed it out. And then when we got back from there, v was still equal to hello because this module, this function, did not change that data. And then we called it again, passing v in, but v got changed to what's up. And so when it printed that out in change2, v is equal to what's up. But then it returned this value. And by returning this value and storing it back into that variable, we have successfully changed the contents of the v variable. So what does return mean? You can have a return statement without data, or you can have a return statement with data. Just like that. And so when I call test star, print out after test star, I'm just going to add an input statement here to block it from running the rest of the code. All right, so when it runs, we see I'm about to return, and then after test star, because it did return. What does return do? It causes that function to immediately leave and for execution to continue running after that line, right? So when we call it, it jumps into here, it prints that out, it hits the return statement, and then it's ready to print after test star, which is what it did. So why didn't we stick return on every one of these functions? There's nothing wrong with doing that. You can put return after every function if you want, as a part of every function, but you don't have to. Why don't you have to? Because if you don't have a return statement, as soon as it hits an unindented line, it returns anyways. So why use a return statement at all? You use a return statement so that you can pass back a value. We could make this thing return a value. Now, if we're going to return a value, we should store that in some kind of result, right? Otherwise, why return it? And so now after test star result equals common result, we'll just see that result was equal to 100 because that's what was returned. We call test start, executes that line. We see return 100. The return 100 comes back, stores that number that was returned into here so that we can then print it out. And we're going to see that it's 100. You can have more than one return statement inside a function. That's common if you have some kind of conditional case, right? So let's allow ourselves to pass in a variable. And then if x is equal to 0, we're going to return a different value for whatever purposes. So if x is equal to 0, we're going to return 0. Else, we're going to return 100. I'm going to take this print statement out. You don't actually have to put the word else in there because it's either one or the other, right? If it returns, great, we're done. If it doesn't return, then it's going to execute this line. But if you really like seeing the word else there because it makes the code easier to read in your head, then that's fine. So when I call test star, if I pass in any number other than 0, then the result's going to be 100. But if I do pass in 0, then when it comes in here and it performs that test, it's going to return 0. So that value is going to be stored in the result. And that's what we see. What if we did not provide a value here, but it was expecting one? It's going to crash. Won't even compile. I guess it actually was running. Is that a compilation error? No, I think that was a runtime error. Anyways, it says missing one required positional argument. One required positional argument. Positional argument. Well, that's that. Missing one required argument. Well, it's there, so it's required. Can you make an argument optional? Well, you can give an argument a default value. I could say that when we call, if no value is provided, then assign 0 to it. I'm going to undo that for now and give that as an example in a different way. Go back to where I was. We're going to write a function that just prints hello followed by the name. So I'm going to call it hi. It takes a name and it prints hello, end quote, common name, right? Return. So down here, when I'm ready to call it, I say hello or hi, and I give it a name. And so now it's going to print hello, Sam. And that's what it did. What if this was left empty? We're going to get that runtime error. Required positional argument is missing its value. Missing one required positional argument. Well, what if we say this? What if we just say our name is generic person? Now it's not going to crash. Now it's going to say, hello, generic person. And so it did, right? It used this value. But what if we pass in a value, right? Sam I am. We're going to say hi. We're passing in this value. So it's going to print, hello, Sam I am. So this is an optional value. Well, it's an optional parameter. It's got a defined variable, it's got a defined value that can be overridden by what you pass in. So this is the default value for that parameter variable. If another value is provided, it will be used. If no variable is provided, if no data is provided, it'll go ahead and use this default value. So why use functions? Provides abstraction. It hides the detail. Allows a person to view many things as just one thing. And my best example of that are things like the built-in functions that Python gives us. I have no idea how the input statement works, how it establishes a connection with the operating system to allow the user to type something in, to get that data, and then return it. Or the print function. I have no idea what magic it does in order to format the data to be displayed in a window on the screen. Or the turtle library. I believe we used the turtle library one day. How in the world did calling turtle.fd or turtle.forward cause this thing to draw a line on the screen? Well, I don't need to know those details. I just need to know how to use it. And so that's abstraction. We use abstractions to refer to the common tasks in everyday life. So, doing my laundry, I can just say I'm doing my laundry rather than give you the list of every task that I have done in order to accomplish that. You know, gather clothes in basket, take basket out to laundry room, toss in washer, add detergent, press start, whatever. There's a whole bunch of steps that has to happen for me to be doing my laundry, but I can just say, do my laundry. And then I know that set of routines, or I can ask somebody else to perform the set of tasks required in order to get the laundry done. So here's a summation function. And lo and behold, it looks like this one's actually tabbed correctly. I must have uploaded the change to it. So summation goes from a lower to an upper, adding all the numbers between lower and upper. So if you pass in 1, 10, it'll add up the numbers 1 plus 2 plus 3 plus 4 all the way up to 10, which will be 55. I've written this code often enough to know that the summation of 10 is 55. And it just uses a loop to accomplish that. So if we call summation of 1 forward, adds 1 plus 2 plus 3 plus 4, which is 10. If we call summation of 50 to 100, then it adds them all up and it returns that result. Now, once this code is written, we no longer care about how it is written, right? Or I can give this code to somebody else and they can import our module. They can use summation with reckless abandon, not knowing, not caring how it was implemented, because there's more than one way you could implement it, right? You could write the loop different. You could write a for loop instead of a while loop. You could make it, start from the upper bound, subtract 1 from it each time, rather than starting from the bottom and going up to the upper, which is what this one does, right? The implementation does not matter as long as it works and it is efficient enough. What does is efficient enough mean? Well, you have to, have some criteria for measuring that. But in a Python program, as long as it's poking along at a reasonable rate and displaying content as soon as the user runs it, or relatively quickly, then it's fast enough. Your general rule of thumb is to write the code so that it works first, and then if it proves not to be fast enough for your purposes, then you go in and you modify it. Because if you try to write the most efficient code possible and you make that your priority, then you'll never get the project done. Instead, you write to get the project done first, and then you look for places where you can improve the speed of it. So functions serve as an abstraction mechanism, hiding complicated details. The idea of summing the range of numbers is simple. However, the code for computing summation is not. It can be expressed in several different ways. So the function call expresses the idea of a process to the programmer without forcing him to wade through complex code that realizes that idea. I guess that's an acceptable way of saying it. I would just say that once you've expressed it in code and it's good enough for you, then you can use it over and over and over without worrying about the guts of how it works. So what is an algorithm? It's a general method for solving a class of problems. It's a series of steps that must be taken in order to solve a problem. The individual problems that make up a class of programs is known as problem instances. What are the problem instances of our summation algorithm? I guess I've skipped past this slide in the past because I'm not coming up with good verbiage for what exactly they're asking here. To me, the problem instance is the specific set of code that we have written in order to solve the problem. And what problem were we solving? The ability to add up all the numbers between x and y, where x and y are provided as values when we call the function. Algorithms should be general enough to provide a solution to many problem instances. So this function here could have been written so that it always did a summation from 1 to 10, right? I could have written it in such a way to just define lower as being 1, and upper being 10. And then every time I called this function, it would return 55. It would return the summation from 1 to 10. So no matter what, but I would not be able to customize its behavior by passing in different numbers, right? It would always do the same thing. That's what arguments are for. They allow the function to work based on data that is sent to it so that its behavior can be modified based on what variables are passed in and what values are passed in. In a well-organized system, each part does its own job in collaborating to achieve a common goal. Functions can enforce a division of labor. Each function should perform a single coherent task. So the turtle library, there's a function that tells the turtle to go forward. There's a function that tells the turtle to turn left. There's a function that tells the turtle to turn right, to back up, to lift its pen, to stop drawing, in other words, to lower its pen, to set its speed, to set what angle it's drawing at, to change its ink's color, to change its thickness. Each one of those is a discrete task. So top-down design starts with a global view of the entire problem and breaks the problem into smaller, more manageable subproblems. Process known as problem decomposition. As each subproblem is isolated, its solution is assigned to a function. As functions are developed to solve the subproblems, the solution to the overall problem is gradually filled out. This is known as stepwise refinement. I'll have to give some kind of examples of us coming up with a problem and then working with top-down design to solve it. I'm going to kind of glide past that for now. A structure chart, a diagram that shows the relationship among a program's functions. Each box in the structure is labeled with a function name. Now, in the programming classes that I teach that aren't to this textbook, we use a different kind of structure diagram. But this is pretty easy enough to figure out. Main calls something called count sentences. A string is passed into count sentences and an int is returned. A string is passed into this function called count words and an int is returned. Then a string is passed into something called count syllables, which uses another function called syllables in. Flesh index, grade level. These are all functions. They all return a value. I'm going to, well, that one's exciting. Main calls the sentence function, which returns a string, and it does so by calling these other functions in order to generate a sentence based on a list of articles, a list of nouns, a list of prepositions, a list of verbs, and so on. So in some cases, you can decompose a complex problem into smaller problems of the same form. A function can be written in such a way that it will call itself. This is known as recursive design. A function that calls itself is a recursive function. Now, a recursive function, the simplest example is this. What if I just called main from here, right? So we enter main, it prints hi Sam I am, and then once that returns, it calls main again. So it's going to loop back in here. It's going to print hi Sam I am again, and it's going to keep doing that over and over, right? Because every time it gets to this point, it's going to recall this function. And this is not a good program. It's going to crash. It's going to print hello Sam I am for a considerable length of time, and then eventually I close the window because printing is actually the slowest thing that it can do, and if it's done off screen, off stage, then it happens much more quickly. So now if I come back and I look at it, then I will see that it has crashed. Maximum recursion depth exceeded while pickling an object. I'm going to have to look up that phrase and never actually noticed that. I wonder how many times we were able to call ourselves before it crashed. Let's find out. Let's have a global variable called counter. Let's just start it off as 0. And then I'm going to add 1 to it. And I'm going to print it out. And we're going to call main again, right? So it's going to keep calling itself. Each time we do so, the global variable counter is going to be incremented. And we're going to get to see how large the counter gets at the point where it has crashed. One thing I must say is that although I have a fast Mac here, idle and Python running on it does not do the output very quickly. All right, here we go. By about, after 1011 calls, it was out of memory. And why is that? Why would that run it out of memory? Because each time, tell you what, I'm going to modify this so that we specifically have a function called recursive, right? So define recurse. It does the same thing. Global counter. It adds 1 to the counter. It prints the counter. And then it calls itself. Just like that. So then when I want, I would call the recursive function. Let me add something to this, though, to indicate why it could run out of memory. What if we had some variable here, and we said x is equal to the counter, right? And y is equal to x plus 1. We're just doing some kind of, whoops, get rid of that semicolon. We're doing some kind of calculation based on the current state of the counter. So when we call recurse, we go in here and we allocate memory enough for 2 integers. And then it does some stuff, and then it calls itself again. Well, these are local variables. These variables are going to maintain their value, just like if we had called another function, if we'd gone up to test star and done something, then these variables still have their value. When we go in to ourselves, a brand new pair of variables called x and y are created. And then when we get up here and we loop back, we jump into the pool yet again, then another pair of those variables are created. And that keeps happening until we run out of memory, because there's nothing that ever breaks us out of this cycle of calling ourselves. Now, we might have said, well, but when I did this, I wasn't creating any new variables. Why did it run out of memory? Because the mere act of calling a function uses some memory. It's got to do something called pushing our data onto the stack. It's got to record where we currently are so that if we ever hit a return statement, we can exit back out, and any local variables that were created will be removed, and it knows what code point it's at. Talking about that specifically, I'm not going to be able to make a good explanation of it in 15 seconds, but there's a call stack. And the call stack looks like each time we call ourselves. The only way I could really illustrate that would be to make a string which contains nothing, and each time we go into it, we add so when I run it, did I not run it? Variable is used before. Okay, fine. I'm getting rid of those things. What is it saying? That the variable is, anyways, that's the most recent change. I had access. Okay, you see what's going on here? Let's see if I can stop that. Stop. Well, fine. I should have been able to hit Control C and gotten it to stop. But you see its pattern. Maybe, maybe not. I'm going to have to modify this a little bit. What we're going to do is we're going to say, if the counter is greater than 10, return. And so you see what happens each time it called itself. It had to allocate more memory on the stack behind the scenes that would allow the return statement to work, and for any local variables that were defined to be released. And this is just kind of a visual representation of that fact that, you know, by the time that we've called ourselves 6 times in a row, we're 6 levels deep. We finally gave ourselves a way out, right? We said once the counter is greater than 10, then start returning. You always have to write a way out of a recursive function. Otherwise, it's kind of like an infinite loop. It's infinite recursion, and you're going to run out of memory. So this is not the best example of a recursive function. It's the simplest. It's not the best. Not a good example of it. When you write a recursive function, there's 2 cases to concern yourself with. One is called the recursive case. When are you going to call yourself? And the other is the null case, when you're not going to call yourself and you're going to start returning out of the function. So you could write a recursive summation method that would look something like this. We're going to take a number in, and we're just going to count from 1 up to x, adding all those numbers together. How are we going to do that? To minimize the amount of state information, to only allow us to only make us use one variable, we're going to use x and we're going to lower it by 1 each time. So instead of adding 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, we're going to add 10 plus 9 plus 8, and so on. So we need a stopping point. When x is equal to 0, just return x, which is going to be 0, right? Otherwise, return x plus the recursive summation of x minus 1. Why did we do that x minus 1? Because if we just called ourselves with the same value, then again, it's going to be infinite recursion, right? Because it will never reach the point where x is equal to 0, assuming we started with a non-zero value to begin with. I'm going to comment out this call because we've seen that that's an infinite recursion. But if I do rec summation of x and I store its result, right? And then I could print that out. That's not going to work because I did not give a starting value for x. Let's just do 10. If I see 55 come back, I know that it worked. Right? And it did. So what happened? It came in here. X was 10. Is x equal to 0? No, of course not. So return 10 plus the recursive value of 9. It comes back in here. 9. Is that 0? No. So return 9 plus the recursive value of 8. Comes back in here. And it's going to return 8 plus the recursive value of 7. 7 plus recursive 6. 6 plus recursive 5, and so on. So I've just stuck a print statement in here to try to give some little visualization of what it's doing. Right? So we went in, we were called with a 10. And so then we called ourselves with a 9. And then we called ourselves with an 8. We called ourselves all the way down to when we called ourselves with a 1. And so then we called ourselves with a 0. That's the point where it starts bailing out. Hope that makes sense. I could do something with the counter to try to make it look a little bit better, but then the code is going to look a little bit more confusing. Maybe I could print called with, comma, x, and then down here I could say print calling with, comma, x minus 1. And here I could just say print returning Now this makes it look like it only returned once. And we know that in reality, it had to return just as many times as it was called. So I guess I could store that result in a temporary variable, print returning comma y, and then return y. Kind of break the step up of where we call ourselves and then return back out of it, so as we can see the numbers increase. Right, so we kept calling ourselves. Eventually we called ourselves a 0, at which point it returned the 0, and then it returned the 1, the 3, the 6, the 10, the 15. Hope that makes sense. The only way I can make it even clearer is if we added in a number of tabs based on the counter. Not going to do it. Just going to leave that alone. I hope that's clear enough. You do not use recursion in your day-by-day, everyday programming problems, so I don't feel like going overboard in talking about it. Another example of it would be just to print out every letter in a string. So we would take a string and we would need to take a current position. And our current position is going to start off being the length of the string. We're going to give it a default value. No, we're not. We're going to set the default position equal to 0, and then it's going to start increasing from there. So if the current position is equal to the length of the string, then we need to return. We're done. Otherwise, we're going to print the string at that specific position, and then we're going to call ourselves again, print underscore s with the string position plus 1. And so it will print the string out letter by letter. This is our recursive case. This is our null case. Our null case is the case that where we start the chain of returns because we don't need to do any further work. And the recursive case is when we still have work to do, so we call ourselves again. So if I call print underscore s and then I pass in some string, we're going to see it print out HELLO. And indeed we did. So recursive function is one that calls itself. You can replace loops with selection and assignment statements with a recursive call. Display range, here's our example of one. Summation, here's writing a summation. Here's their example. I guess they came up with a better one. Print the number of blanks times the margin. Yeah, so they kept a counter that indicated how deep they were into the function, and then they printed the number of blanks to match. So its input was 1, 4, 2, 4, 3, 4, 4, 4, 5, 4, and it started returning its way back out at that point. Infinite recursion is just when it calls itself without any exit being provided, with no null case that provides a non-recursive way to return. The costs and the benefits of recursion. Python virtual machine reserves an area of memory called the call stack. For each call of a function, it must allocate on the call stack a stack frame which contains all the values of the arguments passed in, the return address for that function call, and space for that function call's return value. And then if it continually calls itself with never getting to return, then all of that data is allocated on the stack and nothing ever removes it. Managing a program's namespace. It's about time to stop here. One more thing I want to show is we wrote functions that accepted positional values, right? Define add, and it's going to take X and Y, and it's going to, the result is going to equal X plus Y, and then it's going to return the result. So we could do this, you know, the value is equal to the add of 10 and 20. And then we could print, you know, add V equals, print that result. And press enter. And what's it going to do? Of course, it's going to print 30 because it calls the function 10 and 20 are the values of X and Y. They get added, stored in result, and returned in order to be stored in V so that we could print them out. However, you can also do named functions. What does that mean? I'm not named functions. We can name our parameters. When we're in here, let's add a print statement that says, sorry, I use the old syntax rather than the dot format syntax. But when we call ourselves, we're going to see that X is equal to the value that was passed in, Y was equal to the value that was passed in. Right, and so when we called ourselves, X was equal to 10 and Y was equal to 20. However, just copy and paste those two statements. What if we do Y is equal to 100, X is equal to 20? See there, we've changed up the order. So the second time we called it, Y was set to 100 and X was equal to 20, even though we had passed them in the opposite order. Well, is passing things in the opposite order such a great big whoop-de-doo idea? Not really, but what if you had default values? In that case, you could do something like this. V is equal to add, you know, and you could do that, and the default values are 0. So it's just going to be 0 as its return, right? But you could also say add, let me just copy and paste that. And you could specify, oh, but when you run, you're going to set X equal to 5. And that's what happened. X was set to a 5 while Y was left as 0. Or you could set Y equal to something, right? Y is equal to 999, whatever. And then when it runs, X is left at its default value, but Y is set to 9990. Now, why would you care about that? If you provide default values for all of your variables, then you allow yourselves to use optional parameters. Remember this, where we did print hello, and then we did file equals, you know, and then we gave it some variable, right? Like that. This is an optional variable. If you don't fill it in, the default variable, which causes that print statement to be displayed to the screen, is used. But if you do fill in a file variable, then the print function writes to that file instead. That's about the best example. That's the optional parameter that I think we've used the most, right? That's how that works, is that in the function print that they wrote, they made a parameter, they gave it a default value, and if the default value is used, meaning that the user did not provide it, then, or the programmer did not provide it, then it behaves one way. But if the programmer does provide it, then it saves that file instead. Let's see if we can find the Python documentation for the print statement and see what other optional variables there might be there. So Python print I just want the print function itself. Boy. Pickle bucket. Pickling. I'm going to have to research that. That does not look like what I clicked on. Okay, forget it. That's one example of doing that. Another is when you, no, that was just positional. I'm thinking of when we were using the round function, like we did x is equal to round, 3.14, but I want to preserve one digit. We did that. Well, that's an optional parameter, but it's not a named parameter, but it is optional because if you leave that off, it rounds it to 0 decimal places. But if you provide it with a number, it rounds it to 1 decimal place. So that's an extremely good example, right? Rounds to 0 decimal places, rounds to 1 decimal place, and so on, via the optional parameter, via the optional argument. All right, I think that's a good point to stop. I want to go and show the project lists. I want us to be working on projects. If you get 2 projects done, you can completely blow off the idea of a final. If you get 1 project done, then you get good programming credit, right, as for your homework assignment. So I'm going to be listing some simpler projects in here as well, because I really do want people to accomplish them, to take on at least one of them, hopefully 2 of them. Let's go. Here is just a text file short description of the projects. And like I said, I'm going to be adding a few more to them to encourage people. They are of varying levels of complexity. I will upload the lengthier program explanations. Well, isn't that hard to read? It's almost easier to read right here. Okay, so one of the projects, linked list. Research how to make a linked list in Python. Do it yourself, not using a built-in class that comes with Python. This is the one project where it's okay to use code from the internet. If you want to do this one, I'll send you websites that have code, sample code for a linked list. And your project should use the linked list to add, remove, and to display items in the list as shown in the requirements. So this project does require creating classes. So it's harder because of that, but it's also easier because you can use code from the internet. And since you are using code from the internet, please write a 2 or 3 paragraph explanation in your own words of what a linked list is, right? So you're not just going to copy and paste code and then give it to me. You need to actually convince me you know what a linked list is. Without that, you do not get full credit. Okay, here's another idea. Baseball. The game will use random numbers to decide whether the batter strikes out or gets a home run, etc. You have a lot of freedom in this one. I'm imagining something like this. Welcome to the baseball simulator. How many innings do you want to play? 1. And you know the rules for baseball. If 3 strikes and the team is out. So team 1, batter 1, strike, 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 you're out. That was 1 out of 3 strikeouts. Team 1, batter 2, strike, strike, home run. The score is now 1-0 because the team got a score. Team 1, batter 3, strike, 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 you're out. That was 2 out of 3 strikeouts. Team 1, batter 4, home run. The score is 2-0, and so on. And then 3 strikeouts ends the inning for that team. The other team would then get to play an inning. You can make it more complex than what's shown above. This version right here does only strikes versus home runs. If you want to maintain some state information about there's a player on base 1 and a player on base 2 and stuff like that, you can make it as complex as you wanted. Or you can just make it so that it's either a strike or a home run. Football. Write a football simulator. Use random numbers to determine how many yards the players get each time. If they don't get 10 yards and 4 downs, that causes the other team to get the ball. You could assume the game ends after 60 plays, because it has to have some ending point, right? Which isn't too far from the truth in a pro football game. The ball is actually in play for an average of 12 minutes in a 90-minute game. So only 12 minutes are you actually watching the ball moving on the field. Each play usually lasts about 11 seconds of action. Or so you could just say, I'm going to make it play, 60 turns in a row before it ends. Standard rules of football, you have complete freedom to make the game as simple or complex as you want. Is it going to support passes versus runs? Will it support field goals as well as touchdowns, extra kick points? Would passes earn more yards but fail more often than running? You get to design all that. Hangman. Invent a game of hangman. The computer picks a word and the player guesses letters until they either, well, that just looks totally botched. That's not spelled correctly. Until they either fill the word in or run out of guesses. Let's say 10 guesses causes failure. Or if you think they need fewer guesses to be challenging, go with that. Warning. Quite often in the past, when I offer hangman, people wait until the last minute to try to write it, and then they download code from the internet. This is academically dishonest. Trust me, I can tell. I can usually find the exact site your code came from. Don't do this. I'll repeat, don't do this. Don't download code from the internet for a hangman project. If you get stuck on this and you want to do it, I can give you a flowchart that'll help you do it. It's not a difficult project if you have the flowchart, but try it yourself first. PyFighter. Are you a D&D, Pathfinder, et cetera, fan? I give you simple rules for a game where 2 fighters, they have an attack strength and an armor rating, and they fight it out until one player is reduced to 0 hit points. Or you can make it better. One player did a Pokemon match where the player selected a Pokemon, the computer did too, and then they would, do their attacks on each other, and based on their attacks and which one was immune to what kind of attack. Anyways, it was a cool project. Orcs versus elves. Write a game that matches a list of elves versus a list of orcs following a set of rules that I will post. This one involves lists, probably simpler than the Pathfinder project. I'll post the rules, you'll get to see those. Caesar Ciphers, simple and advanced. The book gives you code for Caesar Ciphers, so you can't just use that. What I want you to do is to write the simple Caesar cipher where you ask for a shift value and everything gets shifted by that value. But then the more complex one involves where they specify a shift value of 10. The first letter would be shifted 10. The second one would be shifted 11. The 12th one would be shifted 13 and so on. So you ask the user to pick which algorithm to use and whether they are enciphering or deciphering. So you ask them, do you want the simple or the complex? Caesar Cipher is another one where people would download code from the internet, or they would just turn in what the book provides. That's why the project gives you guidelines for the algorithms, and specifically you have to implement the advanced one, which is just where the shift value is increased by 1 or decreased by 1 positionally, right? The first one, second one is increased by 1, the third one is increased by another 1, and so on. Password validator. Write a program that prompts a user for a password. And sorry guys, I ran over my time. The program checks to see if the password meets requirements. At least 1 uppercase letter, 1 lowercase letter, 1 digit, and 1 punctuation. If it passes that test, it is then checked against a list of common passwords stored in a file. If any of the common passwords are part of the user's password, it is rejected. So, system administrators tend to pick the password that has the word God in it. And so God is going to be one of the things that are in that file, perhaps. And so even if it passes all of these checks, if the password has the letters G-O-D in it, then it will be rejected. What is the most common password ever? Probably just the word password, right? So you can go and find lists of passwords, or if you ask me for a list of common passwords, a file full of common passwords, I can give that to you. So then the user is told that their password are good, why or why not. In your own project, if you have an idea for your own project, mail it to me and send me a text saying you did so. Make it interesting, not too easy, not too hard. And if it turns out to be too hard, despite your initial prediction, you can always, right, kind of backtrack and do hangman based on the flow chart. But I'd rather you submit a good, honest effort, even if it's not fully functioning of your original idea. All righty. Does that make sense? This looked like a good starting batch for thinking about projects. Hope so. You still here, Jason? Did you have to bail?
Yeah, I'm still here. I just have my mic muted.
Sure. All righty. Well, let's stop here. I'm not going to assign homework based on this because honestly, we already have been using functions. Now, when we continue the lecture, there'll be a homework assignment later this week involving optional parameters so that we have a good, good use of named optional parameters. So we'll do that one on Sunday. Excuse me, on Thursday. Yes, sir?
I'm sorry, I was talking over you. What was that?
I said we'll do that one Thursday. I'll make a homework assignment that covers the optional parameters and named parameters based on that.
Oh, okay. As far as projects, say if I wanted to do like a chess game, how much code can I borrow from the internet? So I was thinking about doing like a GUI interface, kind of like just a normal chess game that you buy on your computer, and just maybe grabbing the code that actually drew that draws a chessboard and pieces from the internet, because I'm not that artistic, nor do I think I have time to actually do that part, but actually programming the computer to do the moves and allowing player input. Would that be acceptable, or is that borrowing too much?
Right. Everybody does research, based on Googling up stuff. And so you could take, pieces off the internet as long as you document, what you took from the internet, which parts are what you borrow, give credit to those, and which parts are your own.
Okay. Yeah, I'm thinking about doing that.
Okay, yeah, that's a really cool project.
Or one Pokemon, or doing like the Pokemon Fighter. That seems pretty cool because there's a lot of stuff available online for that already.
Yeah, that one can be a large project depending upon the number of Pokemon that you implement.
Yeah, well, there's a data science website called Kaggle, and they have the CSV file of all the Pokemon and all of their stats. And it's huge.
Oh, that's cool. That's cool.
So it's there.
Yeah.
And then also there's like Pokemon Wiki that has a damage calculated formula that they actually use. So what I did a while ago was I was trying to use statistics to build a team that average, law of large numbers would do the best job.
Right.
But I had a question. So, so the first question is, when do you think you'll have the test finished graded?
I thought they were. If it's not for you, I will go back and make sure that all the grades have been exported, because I honestly thought they had been. So I'll do that right away.
The ones that are like the manual graded, on my tests haven't been graded yet.
Oh, those haven't been re-upped. Okay. All right. Well, that'll get done extremely quickly.
Yeah, because some of them was just like, type this part in, and it's just like, still has the waiting to be graded part.
Sure.
Secondly, right at the beginning of the course, you were talking about like, kind of like when we were passing our thesis from the variables. So we were talking about our define main and something about the variables between our main program and our other functions. And I was going to see if you could recap on that again real fast.
Okay, please repeat that one.
So at the very beginning, the very first part of the lecture, right after we got done talking about global variables and having to pass the key term global X to change a global variable within a function definition.
Right.
So we created a function called main, in which we were like Fn was Joe and Ln was Bob. Then we have my F2, which is Fn plus space plus Ln. You were saying, well, it evaluates this first before it passes in the function. I was trying to see if you could recap on kind of what was going on there.
Yeah, let me.
About it passes a copy, or I was trying to write down everything and kind of missed what you were saying, which is bad because I could always go back and watch the video.
No. That's fine. That's fine. Okay, so are we talking about what pass by copy means and how that takes into effect, or are we talking about global variables, or both?
Yeah, the pass by, because I understand, like, okay, so if so for example, on your screen, I see x equals 2 is a global variable because it's outside of every function.
Right.
A equals 1 is a local variable because it's defined within a function. And say if we wanted to change x equals 2 to 3 within the first function, my f, then we have to pass a global x. So,
exactly, right. If we're going to write a function that uses global variables, then you need to list every variable that it needs to be able to change. And it's not a bad idea to list even the ones that it's not going to change, in my opinion, just so that somebody looking at the code, thanks keyboard, can look and say, oh, I see what this function does, is it's relying upon a global variable. Once you've done that, then your code has the ability of changing that value, right?
yeah.
And it will change that one rather than trying to create a local variable, you know, of the same name.
So, but if we went back to the main function, if you scroll down a bit, okay, there we go. Let me check mine real fast, make sure I have. Yeah, because I'm getting an error on my end. There's something like some part of the code is not reachable. So we were talking, like, when we changed this, I guess. So is that what you meant? Like when we have our defined main here, it won't. So we have v equals add 10 to, it doesn't redefine in a function, but it just passes a copy into the function. Is that what you were saying?
Well, these values are passed into this function.
Yeah.
And by defining all of our stuff as being contained within functions, including main, we are avoiding the use entirely of global variables.
Okay. All right, that makes more sense.
Yeah, because in the past, our code has been written like this. And we would, you know, recklessly declare our variables. These were actually global variables, so we could call a function and access the value of name, even though it didn't look like we could, right? So if I went into the add function and printed out the name, which I better not, right? Because name is not going to be set otherwise, but I could conceivably print out the value of name, even though it had not been passed in, because this is an honest to goodness global variable, just because due to the fact that it's declared with no indentation, right? If it was declared indented as part of a function, it would not be a global variable, and this would generate an error. So on your compiler in PyCharm, every time you had a variable that had the same name as one of our global variables, it complained about it.
Yeah, it got like a shadowing error or something like that.
Right, and what does that mean? That means that if we did something like this, name is equal to Bob, we are now shadowing, we're masking the value of this global variable with a local one.
Oh, okay, that makes a lot more sense.
And if you wanted to actually be changing the global variable, that's what that global keyword is for.
Okay, that makes a lot more sense about that error now. Okay.
So why don't we go ahead and end this? And if you want to keep working on the syntax error that you're getting, let me see if I can figure out how to reconfigure Zoom so that we can see each other's screen, or you could just send me screenshots, you know, with your phone, and we can figure it out.
Yeah, I think, let me see. I think it already has it where, yes, so share while the other, okay. Yeah, I can share. I have the option to share my screen once you're no longer sharing your screen, I can share.
All right, let me stop the recording.